Hello, everyone. Hello. Happy Saturday. So just right off the bat, I'd actually like everyone with the core team to stand up because what I'm about to present is not just my own work, it's the special interests of myself and all the friends. So please, everyone with Scuba.Tech, half of them are in the back taping. What we're doing, in essence, boils down to three things. We're trying to increase community membership or stewardship with our marine ecosystem. We're trying to promote the fields of oceanography and marine biology, and we are researching new digital workflows that combine historiography with technology. And that last one is what we're really going to talk about today. What you see on the right-hand side is how we do those things. So free and open source research and development. We run events, both public community events as well as private, and we also do training, both with educational institutions as well as internal training. So where do we operate? Here. Right here in our tri-state waters, the upper mid-Atlantic, and I want to give credit where it's due here in the audience with us, Captain Steve and Marine Langevin. They're the ones who said yes when I asked if they needed a deckhand, if I could help haul lines and learn how to crew on a dive boat when I started diving. So this entire adventure began because they let me on board. So this is where we operate. Show of hands, who here has dove locally, whether that be shipwrecks or shore diving? Okay, just over half the room. That's awesome. So what I'm about to show next will make a lot of sense. This is what we're trying to figure out as a team, as a Scuba.Tech team, but I also think as a larger community of technical divers, we're trying to figure this out. On a shipwreck, how do we decode the mystery? How can we share the lessons and the heritage with the world? How can we make it accessible to those not present? By it, I mean not just videos and pictures of the shipwreck, but the experience of being on the wreck, the experience of being part of history with a lowercase h, and being involved, whether that's a classroom on the shoreline working with the dive team, or whether that's exploring a site after the fact in AR and VR. That's kind of what we're trying to decode as a team with Scuba.Tech. Which brings me to what I'm going to talk about today. This is our annual community update. We're going to present three things to the world. This will be also put on YouTube. This will also be put on our GitHub repository. We're going to talk about the Triscopic camera array, which we designed and which Captain Mo got to witness in action in the Carolinas. We're going to talk about surface marine imaging with AMSEAS. And we're going to talk about the Connecticut Aquatic Invasive Species Research Project, which uses machine learning to make a 2-year forecast based on previous surveyed data. So let's start from the top with the Triscopic camera array, which is for high fidelity scanning in low visibility environments. Seems pretty relevant to this area. So let's talk about survey. When we want to build a map of a shipwreck, there's many ways to do it. You have traditional sketching. You have baseline offset and trilateration. That's where you're running tape measures and lines, and you're taking measurements and you're plotting them to vellum and paper. Traditional archaeology is done in this manner, and it works. It's rather tedious. So it's on the glacial side of the axis, but it's still pretty precise if done right. We have rapid real-time survey, such as sonar and LiDAR. And what we focus on at Scuba.Tech is we're trying to push the envelope in this upper right corner. Photogrammetry, Gaussian splatting, neural radiance fields. What they all have in common is they use a sequence of thousands of images taken on a shipwreck, and using differential parallax calculations with stereoscopic projection, you can create points in 3D space. What does that mean in plain English? Really simple. If you put your thumb out in front of you and you alternate which eye you're closing, either your thumb jumps around, or if you're focused on your thumb, the background jumps around, right? If we do a bit of mathematics, trigonometry, and add a few thousand dimensions, that same principle lets us make a map in 3D of the shipwreck. There's some very specific rules for the photos. They have to be a certain distance apart as you're swimming. They have to have a certain amount of overlap, the exposure, the depth of field. It's a 6-week class, and we're not going to cover it. But just know that with a bunch of photos, a little bit of know-how, and a whole lot of compute, you can build 3D models of shipwrecks. One example we're doing here in the Northeast is the Stolt 3D project. Those of you who are on the project, like Dr. Mike in the audience, know that it's been going on for a few years. But I'll show you really briefly some of the outputs we've gotten from it. Using some images, this actual data set was captured by Mike, thank you. We are able to create a very detailed model of the skylight near the stern section. Using this model, we can do census with some of our marine biologists and data scientists to look at the count of anemones, or look at the distribution of clams, or my favorite years are I would have to say scallop years. When the scallops are out, that's my favorite time to do a census. I credit Captain Steve for introducing me to freshly picked scallops. That was a delicious dive. But if we extend the survey, if we swim more, when we do transects, looking down, or what would be known as a top nadir pass, we can derive structural data. So this is the entire stern segment of the Stolt-Nigali. You can see the skylight we were just in. You can see the promenade rising up. So we can derive some structural data. A lot of this is on our website and Sketchfab, by the way, and it will all be open source when the project's complete. I promise there's a point to this lead-in. When we move into the structural data, we can do the same census of the Stolt-Nigali, looking at the distribution of anemones, or I hope the scallops come back. But we can go one step further. By taking slices, we can look at the actual arrangement of the decks on the ship, the rooms. So this is the forward cut of the Stolt-Nigali. We were able to render that recently. If you pull out your phones, this is going to be a very interactive presentation. These QR codes are safe. I made them myself. I've checked them. This links to something, and I'm going to do it right now. This links to something on Sketchfab where you can download this exact fragment, points and mesh and everything. This particular one's a point cloud. Oh, that's big. The network here is going to hate us for about 5 minutes. Anyway, when it loads, you can actually see the forward cut of the Stolt-Nigali, and you can fly around and zoom in, and anyone who's dove on it, you know exactly where you are. So that's a fragment you can share with people. But we have one big problem with the Stolt 3D project. In fact, it's one big problem with traditional photogrammetry. And that's that, I always get voicemails about my car insurance. So the big problem is where we operate. The big problem is that on most days when we go to the Stolt, not most days, hyperbolic, maybe half the days we go to the Stolt, it kind of looks like that. If you squint, you can see the outline of the wreck on that side. Photogrammetry requires a lot of photos with a lot of overlap and good visibility. It requires the diver to, quote Mike, be a human tripod. You have to have perfect camera control, perfect swimming, perfect spacing, and you have to have good visibility. We can't control the visibility, which is a very convenient segue to actually introduce the project. The Triscopic camera array is designed to enable high-fidelity scanning in low-visibility environments. We spent the last year working on this on and off. We got to fine-tune it in the Carolinas. Thank you, Captain Mo. The project designer, to give credit up front, is Sean. He was our engineering intern for last summer, and he took all of our conceptuals and mathematics and turned it into Autodesk CAD models, and even helped us spec out the right parts and materials for assembly. Myself and Henry were the project owners. We provided a lot of the mathematics, a lot of the math for conical intersections of camera paths, and of course testing. The objective is very simple for this project. We want to vastly improve the underwater photogrammetric data acquisition process by designing, building, and testing a Triscopic linear scanning array using a mixture of commercial off-the-shelf and fabricated components. The outputs are what we're going to show you today, and the timeline was last summer, but we've been fine-tuning it since. I'm going to start right off the top with our sketches from the engineering notebook. This is the least flattering possible drawing, but this is what the ideation looks like. We're on a call together, and we're sketching on our tablets. And the goal is pretty simple. We're trying to find intersections of conical arcs of cameras on a linear array such that we can meet the overlap requirements with a single photo, meaning when you look at something, you have natural stereoscopic vision. You don't need to close one eye and move around to find the parallax. You have stereo vision. But in low visibility environments or environments with occlusion, we need more than just stereo. We need triscopic. In fact, we need one camera offset vertically, so we have data in X and Y polarized dimensions in terms of depth. So imagine having a third eye up here, and now you not just have stereoscopic vision in this axis, but now you have it in this axis, which means if there's small gaps in your data set, you no longer lose continuity and you don't lose the dive's data. So the cameras are arranged in a triangle, and this is what it looks like. It's fabricated from extrusion, locking T-nuts, GoPro handles, commodity GoPro cameras, Insta360 cameras. The real work here was done in the math. What's the spacing of the cameras? What are the camera settings? And how can we define that in Metashape to take advantage of these, pre-known dimensions? So we built the system. And what did it look like for testing? Well, We worked with the NOAA James J. Howard Marine Sciences Laboratory that's in Sandy Hook. They have a very cool test dive tank, good visibility, obviously. Adjustable lighting is super cool. They have adjustable color temperature as well as adjustable angle and intensity, so you can simulate any lighting condition in this test tank. High chromatic visibility, which is to say you can see colors down there. And we have a controlled artifact field. So while we installed the system on the ROV, we had the system field testing on an ROV, so we could have it stationary for hours at a time underwater and focus just on the data and the methodology before we moved it to dive trials. As a side effect, it lets you put it on an ROV, so you can go into really hostile or deep conditions that a dive team might not be effective in. So this is Henry driving it at the James Howard Laboratory. He also looks really cool in that photo. That red lighting was not put there for show. They actually have like a dive mode where all the building lights power down and the red lights come on and it's all red underlit. And it feels like an action movie, and the science was real though. So this is us. You can see the perspective of us looking through the viewport. Kira painted up a really cool artifact pot with the NOAA logo and their mission phrase. And then you can see Henry's viewpoint from the control station. But let me show you the output. On one test dive, with one camera failed, we were able to image the entire dive tank in, what was this, a 10-minute pass? So in about 10 minutes, we were able to capture the entire artifact field as well as the geometry of the dive tank. But I do want to give a sincere thank you to the James J. Howard Marine Sciences Laboratory. If you get the chance to go to Sandy Hook, it's really worth checking out. We will continue to work with them as time and staffing allow. We then moved on to our prototype test in confined water. This was at a pool at a dive shop in South Carolina. Mo knows exactly where this was. And I'm pleased to report, and the reason I'm including this is the system trims neutral. I know it looks very bulky. The reason we used a particular aluminum extrusion of a particular size and the handles we did is that it's neutral in the water. So when you're holding it out in front of you diving, there's no pivot, there's no effect to your trim whatsoever. It's very hydrodynamic, and then it clips off to the side, and it streamlines. It ends nearly at your fins, but it will streamline to your side. So it's good to travel with when you're going to and from the site. We then moved to operational testing. This was at the site of the Charleston tug. The conditions were more challenging than we expected, but that ended up being a good thing, a trial by fire sort of thing. We had heavy current, very low vis, 3 to 5 feet. We were between 2 hurricanes. Heavy churn. I would say my VVI was varying by 10 feet plus or minus. It was wild. Low light and no chromatic variability. It was different shades of teal. In fact, it looked like that. That's a still photo from the data set. But I'm very happy to report that when we got back to the room that night and we did an initial crash alignment from the rig, we were able to get data. The Triscopic does well in vis as low as 3 feet, which was better than our calculations expected. So this is the stern of the upper deck of the Charleston tug. You can see us passing around the stern. You can see the data set from all 3 cameras. And because that center camera is further forward on the rig, because you're holding it like this swimming, the center camera leads, it's able to capture contextual data that aligns the 2 side cameras. Let's take this data set around the front. We were able to capture the entire top shell in one dive. The conditions were very challenging, and yet we were able to get a full data set in one dive on a beta trial. So there's a lot of talk, but it's probably cooler if you get to see it for yourself. So if you pull out the phones, this is open source. You can keep the model. You can download it and have the actual point cloud and the mesh and everything. And if it doesn't work, send me an email, and I'll zip it and Dropbox it to you. But if you scan it, you'll get the top shell. It's decimated. It'll look a little chunky. That's because I'm trying not to put 4 gigabytes on your data plan. But there's the shell. You can fly around it. If you're on an iPhone and you tap the air button, you can project it on the table and walk around. And I want to give thanks because intern Sean is now student explorer Sean. He was nominated at the end of last summer and obviously approved, and he's now a member of our team. So Sean went from a high school intern to one of our marine engineering student explorers. So thank you to Sean. This is just a copy of the certificate that we give all the interns at the completion of any successful project. And that's a photo because he did all the design work. But we like to give back to the community. Everything we do is open source. So if you scan yet another QR code, these are all the CAD files. It goes right to our GitHub, our repository of all our design, all of our R&D. There's the GitHub repository. So you can build one yourself. And if you're having trouble or you want photos from all different angles, send me an email. The last slide will have the email. And I will send you an entire photo album of every conceivable angle and where we got the parts.
Get ready for 20 gigabytes.
It's big. So I just showed you a whole lot of stuff on the next iteration of making underwater models. Yes, we are applying it to the Stolt 3D project. I'm really excited for this year's dive season. But we can take it above the water too. And without further ado, I'd like to introduce Henry Tippins-Richin.
Surface marine imaging with AMSEAS. So I've been a volunteer with AMSEAS for, Robert, about a year, maybe a little less, a little more. So I take pictures, scientific photography. So what I've been up to recently with that is trying to create relevant 3D imaging for necropsies. That's sort of like autopsies, but on animals. So testing was initially done on this dolphin skull. Credit to Dr. Joy. She's an anatomist at Mount Sinai. If you scan this QR code, you'll be taken through a 3D model of a dolphin skull. It's a fairly safe image. There's nothing gory about it. Leave that up there for a second. So with this technology, we're able to take two sides of the dolphin skull and stitch them together. And the only real way we're able to accomplish that is because of the precision that we rely on with the software we use and the skill set we've acquired. So we're able to scale the models down to about 1/10 of a millimeter. So you can go in there after the fact with scientific instruments and measure it like you would with calipers. Really important if you're trying to get a feel for certain nicks and cuts or average tooth length or any kind of science you can do with measurements like that. Then, after that proof of concept, we moved into the dial M for marine mammal. This is the real deal with an actual deceased whale. So, yeah. The body washed ashore. It's a juvenile minke whale, and the clock is ticking. When whales wash ashore, they start to bloat. As I'm sure you all know with dead bodies, they start to expand. And that's fine with smaller mammals. I mean, it's gross, but it's fine. It happens. But with a whale that weighs tens of tons, this can turn into a bomb. So it's very important to start taking the whale apart, taking samples, and getting it buried. It's a public health concern as well. So how do you capture the entire whale in one go? And I think all of you know the answer. It's photogrammetry. So sorry if this is a little gross, but here we have the whale as it lies. And with the photogrammetric process, we can look all around it at once. And yes, with all the measurements we have and the accuracy we have with the scaling, we can go back after the fact and start looking at the various abrasions and cuts and injuries that the animal might have suffered. Then that can go to researchers, and they can use it to further study the whale that is in pieces under the sand. Feel free to scan the model if you want. I understand if you don't on this one. But again, with all of our stuff, it's open source and available to the public. What is the impact of surface marine creature survey, and how can we help? Well, I think I answered that pretty well. Giving researchers another tool. The photographs are great, by the way. Scientific photography of the site, it works very well, but it can be a lot of images to sift through. So having one complete image and having all of that context at once really creates a good platform for researchers to study. And with that, I'll hand it over to Robert from AMSEAS.
Well, thank you. I work with AMSEAS, and I've been fortunate enough to work with Henry, and I was just thinking in your last picture, you are tall, but you're not that tall when it comes up. So you can see the 3D image that we might not be able to get. I'm going to talk a little bit about what we do with the Atlantic Marine Conservation Society. I've been doing marine mammal and sea turtle work for the last 35 years, and as I was sitting here, I was thinking about all this technology, and I remember having conversations saying, wouldn't it be great if someone could take a picture of an animal and send it to us so we wouldn't have to drive all the way upstate to find out about it? And here we are now getting 3D models, and some of the things that we see now are things that we wouldn't even actually be able to record. You can see here we have a turtle on the left-hand side. We do this with public support, volunteers, students out walking the beaches. On the right-hand side, that's also a minke whale. We actually look at this from the perspective of there are marine mammals and sea turtles in all waters, but we don't have a great understanding of how many are here and when they're here. We just know that you guys are out there seeing a lot more. And so I'm going to do a real shameless plug of saying, if you see something, you go, I wonder if anybody wants to know it. We do. So just let us know what's out there, because everybody's going to ask, is this unusual? Of the species of large whales, we have right whales, fin whales, humpback whales, minke whales. In recent years, that's changed because we're seeing a lot more of the humpback whales. The fin whales and the minke whales, fin whales are very quick. They're second largest animal to live on the planet. So you usually don't see them as readily as you would a humpback that like to breach and fluke flap and things like that. But the minke whale is a lot smaller. You saw from that image, they're the ones that are usually missed. We're in the middle of an unusual mortality event for these animals since 2016, which means we're having an increased number of animals that are washing up on our beaches, and it's for different reasons. So the humpback and the right whale are both in an unusual mortality event related to vessel strikes and entanglement, whereas the minke whales are related to a biological process. It's actually more of an encephalitis. So us being able to do an examination is really important. We also see dolphins. This is a Rizzo dolphin, which you usually see off at the shelf break. They feed on squid, usually deep diving, but we do see these animals. We see common dolphins on the bottom and bottlenose dolphins, and it's becoming a lot more common in our waters. So we have 4 species of seals that we encounter, and to this point, Gotham Whale noticed that we're starting to see seals south of the Verrazano Bridge many years ago. What's really interesting about that is most of the time, it's finding out where animals are showing up, because you see them first, and then groups go out and we start to do surveys. So we have harbor seals in the top right, we have gray seals, we have hooded seals, which are really cool just because they're weaned in 4 days, so they get to be like 100 pounds in 4 days. That's really cool. And the harbor seal on the bottom right. We also, of the 7 species of sea turtles found worldwide, we get 4 of them in our waters. The leatherback is on the top left, loggerhead on the right, green on the bottom right, and the Kemp's Ridley, which is most endangered. These are animals that become hypothermic or cold stunned in the fall. Our facility in West Hampton Beach is a critical care facility for sea turtles for any other network members. So we don't just deal with New York. Our focus was really to say, what do you do when your lawnmower runs out of gas and your neighbors aren't around to help you? You need to actually have someone else. So when I was at Riverhead Foundation, we were the only group in New York, and now we have multiple groups, just like Gotham Whale out there doing research, so that we can kind of share and build that capacity, because although Long Island is only 130 miles long, it's still hard to get to a lot of places. And so that leads us to what we saw. This is a humpback whale that washed up in the Rockaways at the beginning in 2017. And you can see from these images here, this is basically the best work we did. That's why we like Henry. Not just that reason, but you're all right. But we basically were able to get a lot more information than what we would get. In this survey here, I've talked about how we grow and building partnerships. There was 5 of us on that beach doing a necropsy. You need about 15 to 20 people to be able to do this effectively in a couple of hours. Giving the example, this is a whale that came up in New Jersey, a humpback whale, and they decided to move it off. And you can see they're pretty heavy because that's all the equipment that was needed to move this animal off site and then be able to do that. Times we do them on the beach and we'll do a necropsy, and as Christopher was saying, that it's kind of gets to be gross, if you will. We call it a gross necropsy, not just because it's gross, but it gets us basic information. And then the rest of that information is actually passed on to our pathologists, and then they look at the tissues and everything else that we take. But the key is getting the access, and that comes from a team effort. You really can't, you just don't have 20 people sitting around going, hey, let's wait for us to go out for a dead whale. I mean, that's, besides the fact it's pretty morbid. But we also have a lot of activity. Give you an idea of the shipping going on. The one thing that I always say about whales when you see them close to shore and you can go out, which is something that's very different than 20 years ago. When I used to go out on a dead whale response, most of the conversations would be, I had no idea whales were here. And I would always say, hey, have you ever heard of Cold Spring Harbor Whaling Port? And they're like, yeah. Have you ever heard of like Amagansett? Yeah. Have you ever heard of Sag Harbor? Yeah. Well, do you think they put those ports where whales were not? They were here. So in that case, as we protect these animals, we would hope to see them. Now we've had changes in food abundance and menhaden, so you see them closer to shore. The one thing we know happens if they're close to shore, they've gone through shipping lanes, and that's a challenge. Like me at a buffet, I might bump into you. I'm not necessarily going to pay attention to that. So you want to make sure that people know they're here and report what you're seeing, and then we can kind of talk about it. And this goes to fin whales. Here's a fin whale. Everybody likes this picture. Awesome, right? Everybody sees the common dolphin riding the bow wake. So the interaction is really cool that we start to see some things about these animals. This is what we started looking at whales for back in the 80s. It was the fin whale that we looked at mostly. Humpback whales now, I do aerial surveys counting seals on the east end of Long Island, and almost every survey now I see a whale. Dolphins, I mean, here's a bunch of dolphins that we see, so we're seeing a lot more activity. The more we know about this, the more we can start answering the questions that you have, because although whales and dolphins and these animals wash up, it's really the proportion of the wild population that we want to understand. You know, is this 100% of the animals or is it 10% of the animals? And we only know that by saying, hey, are we having other sightings? In recent years, we've actually we've gone out and we've seen other whales swimming offshore when we're conducting a necropsy. And so that's really a big change that we want to be, and that's a positive that you would hope that you would see these animals here. Seals are a big thing. I want to point this out. Any marine mammal you see, you should stay 50 yards away, stay back from them. Keep in mind, a whale outweighs me, and so you just don't usually mess with those things. But they don't necessarily know what we're doing, so give them as much space. Usually whenever I'm on a boat, we just go dead in the water and see what the whale does. We're doing a project here in New Jersey where we're doing some seal health assessment work, where we're actually trying to capture seals, and then we put satellite tags on them, and unfortunately, we only finished capturing them, what is today, Friday? Saturday. Okay. On Tuesday, so I don't have the tracking maps up there, but more than happy to show you guys them later. But we have a number of animals that we track moving up and down the coast. One of them has actually just started moving north, so it gives us information on what they're doing, and then looking at things such as avian influenza. We've been working with our colleagues in Alaska. I worked on a project with NOAA where they were looking at some of the imaging and looking at some thermal imaging. This is looking at them on ice, so they stick out a lot better. We're trying to see how that might work. So using technology is a big tool for us. And the big thing is, how can you help? First thing is report what you see to our stranding hotline. We should have checked our QR code before we done this. So maybe that works. If not, come see us at the booth. But stay back from these animals. Understand these animals are here. We do beach cleanups, beach monitoring. Most of the marine debris that we pick up is ingestible. Thank you.
CT-AIS, which is the Connecticut Aquatic Invasive Species Research Project. It's machine learning for invasive species prediction. And this project is being done by one of our new student explorers, Getty Lucier. He is a data scientist student with UPenn, and he has a fascination and appreciation for marine ecosystems, marine biology, statistics. And what a great combination, because we're currently trying to tackle invasive species in Connecticut freshwater bodies. Specifically in this study is Candlewood Lake. And Getty was here yesterday, but today he's actually back at UPenn. He's back in Philadelphia. So he recorded his segment. It's a 10-minute video where he walks you through not just what we're trying to solve, but the tools he uses, how we do it, and some of the predictions we got. So for the next 10 minutes, Getty's going to present, and after that, we'll wrap up.
Everyone, my name is Getty Lucier, and today I'll be presenting my work, Machine Learning for Invasive Species Prediction on Candlewood Lake, Connecticut. A little bit about me before we start. I'm a junior at Penn studying political econ and environmental management. I have a love for fishing. Aside from the amazing community at Scuba.Tech, I was driven to do this project for my love of fishing and conservation, and I joined in January, and I'm hoping to put my data skills to good use. So let's define the issue. Zebra mussels and Eurasian water milfoil. So Eurasian water milfoil and coontail have significantly impacted the lake's ecosystems over 2007 to 2020. Now recently, 2020, zebra mussels have been discovered and factored into that mix, and they pose a potential for rapid colonization, which will surely threaten aquatic biodiversity and infrastructure. So it's important that we have an early detection and prediction method to help the Candlewood Lake Authority target certain locations for targeted intervention and removal. All right, so what's the plan here? So we're going to collect the data and prepare it. We're going to take all this information from Candlewood Lake, the Candlewood Lake Authority, and we're going to integrate their zebra mussel sightings data. We're going to create synthetic data for where years haven't been observed, so that's 2021 and 2022, specifically years where zebra mussels were sighted and first discovered. We're going to build a machine learning model to do this. I'll explain that later. And finally, we're going to build a classification random forest model to estimate conditions for zebra mussel populations. Plain English, that's basically like, where do zebra mussels like to live? All right, so I'm using RStudio, love it for a variety of reasons. It has a ton of these libraries that I've listed below. and I'm using it for data analysis, statistics, and visualization. All right, so here's the transect data. It's from 2008 to 2020. It's unfortunately unaggregated and in PDF form, but it's organized by transect and point, which is the group and point, and it comes with latitude and longitude coordinates, and it has a couple of important relationships we want to look at, that being depth, substrate, species, distance from shore, etc., etc. Now, to convert this PDF image into an actual working document or a CSV, I've designed an optical character recognition algorithm to enhance the resolution and then convert it to text. Now, if you're doing this from the GitHub repository yourself, I strongly recommend that you start after I've already cleaned the data, because there's a lot of tiny errors like you can see right here that the optical character recognition couldn't catch that I had to go through and manually clean. But let's get started. So here is our time series analysis. What I want you to notice from this graph is that Eurasian water milfoil strongly dominates the total population each year. And I want you to notice how the other category, which is essentially every other species that was infrequently monitored, unfortunately the Candlewood Lake Authority didn't consistently monitor the same species. So that's all combined into one statistic, and we're using it for analysis later. Right, here's the same information, just in map and pie chart form, so you can see different growths in proportions. So now we need to create some synthetic data, right? Why? To augment our limited real-world examples. We have around 1,260 data points over 12 years, and we want to feed the models more data to have more robust and more accurate predictions. And so what we're doing is we're basically building random hypothetical scenarios using the jitter technique. Right here on the right, we have a very crude map of what it looks like. As you can see, for every red point, there's a couple of blue points around it. And that's basically what the jitter looks like on a map, right? So I move a point to slightly to the right randomly, right? And this point is 0.1 meters more deep, or 0.1 meters less deep, etc., etc. And we're basically trying to fabricate random points at random depths, etc., and random variables to give the model more scenarios. What I'm using for the Eurasian water milfoil is a iterative random forest. Basically, this builds hundreds of decision trees and subsets each one of them. For each tree, the majority is taken in this scenario because we're using a classification model, and going forward with that. Now, my random forest builds on a subset of training data. So we're taking what the subset, or 80% of the data in 2008, and we're seeing how well that predicts 20% of 2020 data. Now, that obviously shouldn't be very good, but once we start to factor in 2008, 2009 data, that should be a little bit better. And then once we start to build in 2008 through 2010, that starts to be even better on top of that. Now, that just helps incorporate yearly trends into the model. All right, so working with other species predictions where the variables may not explain the situation as well, we're using a lasso regression to shrink the unimportant ones to zero. Now, iterative technique as well, but as you can see in this bottom bar, the mean standard error goes down from around 20 points out of 26 points. So that would have been horrible predictability, down to around 1, right? So that's like 5% error versus like 90, right? So that's how we did it with the coontail and others, just because the variables may not have explained the entire situation of their population. All right, so incorporating zebra mussel data, due to the difficult nature of zebra mussel calculations, that is, you either see 1 or you see 1,000,000 or more than the eye can count. I've gone through both of these data forms, and I've created basically, are they there or are they not there? So presence or absence, right? I'm going through and I'm populating another data set that way, and this is this alongside the synthetically created data for 2021 and 2022 will help me build my final model, right? So limitations to consider. So the original species data, that is MUIR-SPE, or Eurasian water milfoil, and SURDEM, those are observations. That means a surveyor is going out on the lake and they're visually deducting the proportion of how much there is. So that's not as objective as pounds, ounces, and it's really hard to tell consistently year to year just by eye, right? With machine learning models that we've just built, the more fabricated data that feeds the model, the less accurate the next prediction will be. What I mean by that is 2021, I have a good deal of confidence in, just because all of the data that went into training the model and then predicting based on new points was real data. That was all from 2008 to 2020. But once we start moving to 2020 or trying to predict 2022, that becomes a lot less accurate, because 2021, or part of that training set, is fake data. Mean absolute error and mean standard error are averages. Some points could be much more off. That's just something we need to consider with all machine learning models. And then, as I've stated before, zebra mussel counts are hard to quantify, either one or more than the eye can count. And zebra mussels, the bathymetric data is based on the nearest ecological data point. So I took data from the original transect data, and basically whatever coordinate was nearest, I use that to populate the substrate, I use that to populate the depth, and etc. And that may not be as accurate or as true to the point. It just assumes that the bottom of the lake remains relatively constant in certain and similar areas. All right, so going to the actual model, we have great predictability of presence and no presence. We have a very small error rate, which means we've nailed it on the head. We can go into more what each point of the random forest means later, but here are the points that most feed or are most impactful on the random forest classification. Right below, we have a mean decrease in Gini, which is basically how pure or impure a node or a part of the tree is. What you need to know is that temperature, Eurasian water milfoil, coontail, and the dew point have the greatest impacts, while the other points are less impactful, right? So we can see directionality using these graphs. As temperature goes up, it's more likely to classify as present. Some Eurasian water milfoil points are good, but more than 10, it tends to decrease. I'll just skip through these really quickly. And finally, what can we conclude from this? So temperature, other than species populations, and dew point tend to have the biggest impact. Our model predicts that some Eurasian water milfoil and coontail is best for zebra populations, but too much could be bad. Areas that might have dense vegetation could reduce water flow, light penetration. Zebra mussels may not enjoy this. As temperature and dew point increases, so should zebra mussel populations. And my prediction is that this has to do with water chemistry, which there's a lot of literature to support that. And shallower depths are more preferred, especially when they are softer. And we need to interpret all this information together. These are not separate data points, and not one data point can immediately classify. We need to take all of this together. So what have we done here? We can get a good estimate of where zebra mussel presence are on the lake. We can create synthetic data estimates using past year's data, although very limited, and according to statistics, zebra mussels have certain depth, substrate, temperature, and neighboring species presence. Thank you so much for your time. I have attached my GitHub repository below, and my email and my school email if you want to reach out to me, and I greatly appreciate your time. Thank you so much.
First of all, thank you very much, Getty. He's not here in the room with us, but he will be watching this video, so he will get your applause. He worked very hard for, I'd say, 3 months to let us do 2 things. Number one, we were able to confirm the conditions, whether that be substrate, depth, temperature, that different invasive species thrive in. And number two, he's been able to validate a new methodology where we can look up to 2 years into the future and see if the conditions match where those species will be propagating. So everything that was just done will be open source. If any of you know people who are working with marine census data or working on it yourself, You can get the repository, or you can send an email to hello@Scuba.Tech with any questions you have. We're at booth 331. Look for the giant swimming pool with the ROVs. We have a dive tank, and you're all welcome to come by and actually go diving with the robot systems. We have all the cameras online. We're going to be doing some TV hits later. You're welcome to stop on by. We're also going to have AMSEAS at the booth, and they'll be able to do Q&A and give literature and talk about how you can help our local seas. Thank you all for your time.
Thank you.
All right.